Well, good afternoon, everybody, and thank you very much, Professor Senthil Velan, for asking me to say a few words um, at this today's event. Uh, what I wanted to actually, first of all, start by congratulating you on having completed 75 lectures in this series. But I didn't want to congratulate you for merely organizing these lectures. I think you have done something remarkable at this point in time. Uh, in the last 4 years have been a time of fairly widespread suffering, misery all over the world. If not actual physical suffering, there's been a lot of inconvenience caused to everybody. But we have learned two things. One is to make the best of the situation. It's Shakespeare a long time ago, sweet are the uses of adversity. And we have learned that in the adversity that the pandemic brought us, there are some positives that we can do. And the first positive really is that we are able to connect over long distances in space at the same time or even at different times. So space time becomes something that we really are playing around with. The entire world has got connected thanks to remarkable inventions like Zoom and Google Meet and all these other modes. Uh, but it's not just the invention of certain technologies. I think uh, we've got comfortable with this mode of interaction. At the beginning of the pandemic in 2020, everyone was complaining, or a large number of people of my age were complaining about, how they miss the human contact, how it's so difficult to lecture to a class when you can't see the faces and the reactions and so on. All of it is true, but we learned how to use telephones. We learned how to use letters. We've just figured out that when you want to communicate, you can communicate. And I think that is one of the very positive things that we've learned in the last 3 years or 2 to 3 years that we've been having this kind of isolation. No, of course, there have been very bad things that have happened. A lot of people have passed away. A lot of unnecessary deaths have happened. So, and so the price has been considerable. Anyway, regardless, I think that I would congratulate Professor Senthil Velan and his colleagues for actually seeing an opportunity and being guided, I feel, by the desire to make sure that students did not lose out in any way, or at least if students did not lose out as much as they did by isolation, by bringing people to them, by bringing discussion, by bringing seminars. And I think to do this over a period of a year and a half uh, has been remarkable. I think the what you have done, Professor Senthil Velan, uh, is more than just bringing seminars to students in Trichy. You have brought seminars to all of us from all of us. You've really made a community, a virtual community, but one that is very vibrant and that is valuable. This kind of connection has been extremely good. Uh, and now, because you have all these video lectures videographed and you have them stored on YouTube, you actually have an incredible resource of a catalog of the kind of work that is being done in the area of nonlinear science, more generally, in the area of complex system studies, in this 2 to 3 year period. This 2 to 3 year period has also been remarkable in another way. The first Nobel Prize in complex system studies was awarded in 2021. The pandemic taught the world that, climate change is real, that complex systems are really very important. And I think the realization that these studies are a new type of physics has been extremely influential. The world has learned to take note of it. And it's not just because, we've been doing this business for the last, 30 or 40 years, and the world is picking up. I think climate change is not only real, it is going to have very significant effects on humanity. And the problem is intrinsically nonlinear. The problem is intrinsically complex in the way in which we understand complex systems. One can go on talking about complex system studies, but what I thought I would do is to send a link to a very interesting video and an interview that was carried out by Ginestra Bianconi, where she interviewed Giorgio Parisi, the Nobel laureate who was awarded in 2021 for his contributions to complex system studies. There is a journal called the Journal of Physics Complexity, and the latest issue contains two articles that would be of interest to this community. The first, and in a sense the more important one, is Giorgio Parisi's thoughts on complex systems, an interview with him. So I'm going to send a link to you, Professor Senthilvelan, for you to share with everybody in this group and in general in the other group. So in this particular interview, I'd just like to quote a few things. Because this is relevant to the 40 others, students who are there and in the department. Ginestra asks him, you're famous for being much loved by your students and your collaborators. What is your advice to young researchers in complex systems? So what Parisi says is, my advice would be very similar to the one I'd give to those who do not work in complex systems. Basically, try to understand, first of all, what are your abilities, and try to profit from your capabilities at their best. I think it's important to be confident in yourselves, to study problems that are difficult, but this is something that is true everywhere. And here is the part which I would like you to pay particular attention to. He says, I think that one should try to look to some interesting problems and try to take some risks. Of course, you take risks with moderation because one should not take too big a risk. I mean, trying to solve the Fermat theorem for 20 years without succeeding, although now it has been solved. But I mean, in the past, that would have been quite frustrating. So it is good that you have to understand which things you can reach and which things you cannot reach. It's important to have a positive attitude, and above all, to remember that you should look at interesting problems and try to take risks. Well, I hope that the students who are listening in today are inspired enough by this amazing set of 75 lectures that Professor Senthilvelan has put together. All the important researchers in India or a very large number of the important researchers in India have been covered. And importantly, you've brought to us researchers from all over the world who find this a valuable resource and a great inspiration. So let me conclude by congratulating you again, Professor Senthilvelan, and congratulating Bharatidasan for having taken this initiative, and wish you many more, a longer period of this online existence for this set of lectures. All the best.
Thank you, sir. Thank you very much for your blessings and wishes. So now it's time to start our lecture. So I would like to introduce the speaker formally to everyone. So, good afternoon to everyone. I welcome all of you to the 76th lecture in the lecture series in Nonlinear Dynamics, conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. It is my pleasure to introduce today's speaker, Dr. Suchetana Sadhukhan from Vellore Institute of Technology, Bhopal. Dr. Suchetana did her MSc at NIT Roorkela. She carried out her PhD at IIT Kharagpur, which she completed in the year 2018. She immediately moved to Institute de Ciencias Físicas, UNAM, Mexico, and continued her postdoctoral work for 2 years. She then came back to India and joined in the present position at VIT Bhopal, I think 2021. Yeah.
Yes.
Yeah. Dr. Suchetana works on random matrix theory and econophysics. She has delivered a large number of talks and published very good number of papers in the field of her expertise. I met Dr. Suchetana recently in an annual conference held at New Delhi. After hearing her talk, I decided to invite her to deliver a lecture in this forum as well, so that many more students will get benefited. When I inquired about this possibility, she immediately gave her consent to deliver this lecture. Thank you, Dr. Suchetana. With this short introduction, now I invite Dr. Suchetana to deliver her lecture. Over to you, madam.
Thank you so much, sir, for the introduction. And I really feel honored that you have given me the opportunity to present here in this nonlinear dynamics specific group. So just let me share my screen.
Yes.
Is my screen visible?
Yeah, you can go to full screen mode. Yeah, that's it.
Okay, so today I'll try to explain the econophysics, or I'm not an economist, so I'll just try to explain the financial market that we are all familiar with, the term share market or stock market. So I'll just try to explain financial market from a physicist perspective. And these as Senthil Vanel sir already told that during my PhD I was working on random matrix theory, so I moved to work on this real world complex system during my postdoc tenure. So this part of the work what I am going to present, that I have done during my postdoc with Professor Thomas Seligman, who is a professor at UNAM, Mexico. And this work is also in collaboration with Professor Anirban Chakraborty, faculty in BML Munjal. Hridesh Kumar Farasi, he is also a faculty in BML Munjal, and Paris, a postdoc student at UNAM, Mexico. So to start with, first of all, what do we understand when we say financial market? So there are two groups mainly. One is buyer and another is seller. So buyer will try to sell the asset at highest possible price, and uh, seller will try to sell the asset at the highest possible price, and buyer will try to buy at the lowest possible price, because ultimately they want to have profit. And once they interact during this buying and selling their asset, they continuously interacting among themselves. And what we have a time series of stock prices. So it is a continuous evolving process. So we can have a daily time series, we can even have intraday time series, because at every moment it is evolving. So this kind of data set is very much complex in nature, and it is very much interesting to understand, because understanding the time series is important if you want to gain profit, or if you want to see the or understand the trend or the drivers which are affecting this time series. So that is the motivation for doing research on the financial market. So we have the time series of stock prices, and the daily data set that is freely available on various website like Yahoo Finance, Google Finance, or Bloomberg, Quandl. But although the intraday time series is not freely available, if someone is interested to do research on intraday financial time series, they have to pay and buy the data set. And so here for the current work, I will focus on the daily time series. And we have the we will consider the closer price means that the price with all the stocks, uh, means the price of the stock at the end of the day. So that is the closer price. So here I have shown one example of the closer price, and you can see that it is having an uprise trend. So what we'll consider for the further calculation or for further analysis is the log return is just the current day price, the difference between the current price and the previous day price. And we'll take logarithmic return is the natural logarithmic of the current day stock price minus the natural logarithm of the previous day price. And the benefit of taking logarithmic return over the simple return, this is the relative return. So one can work with the relative return as well, but the benefit of taking the logarithmic return is that it is simply additive in nature. So if you want to calculate the logarithmic return over multiple time period, it is just the additive. And whereas that is not the case for the relative return. And here if you just work on the multiple time period, that will introduce compounded error. So for the time or for the research, we normally or the research community normally prefer to stick with the logarithmic return. And another benefit of using the return is that you can see that it is having a price trend, and where you are considering the logarithmic return, it is kind of means it is normalized with mean zero, and it is having fluctuations symmetrically at both the sides. So now we have the normalized data set. So we are having multiple stocks, they are having different kind of time series. Now what to do with the time series? With a very simple example, you can understand that, say if you are sitting at the McDonald's and you are enjoying your burger, that means that will increase the sale of McDonald's. And that is you can easily understand that that is correlated to the Coca-Cola uh, stock prices as well, if you are sitting at the McDonald's. So there are a relationship between uh, companies or between the sectors. So what is the relation, at what degree they are related to each other, that is important to understand. So to understand that, what we can do, that we are having one statistical tool, that is the Pearson correlation coefficient, that gives us the that helps us to quantify the degree of the relation between the different sectors or different stocks. So I'll not go into the numerical or mathematical form of the Pearson correlation coefficient. So once I have the time series, once I have calculated the Pearson correlation, I'll have this kind of average correlation matrix between the sectors. So these are the abbreviated form of the sectors. So each sector is having multiple stocks. So if I now concentrate on the average correlation matrix, so say this block says that how companies within sector are correlated to each other. If the correlation value, the minimum can be -1 and the maximum value can be +1. If it is having higher correlation coefficient, that means if the variables, if the correlation between two variables is showing higher value, that means they will move in the same direction. And if they're having negative correlation or the correlation of -1, that means they will move in the opposite direction. So one is that the stocks within the sector, they can be correlated, so we'll say intra, and they can have the relation with other sector as well. See this one, that is the financial. So financial, you can see it is having higher correlation value because it is almost red in color, which from the color word you can see that it is having higher correlation value. So they are correlated among themselves. But if you see that how financial market or financial sector is correlated to energy sector, that is this block, and you can see it is having almost a very low positive correlation, means they are having a relation but that is not that much strong. So this is how we study or we infer the information from the correlation matrix. Of course we will have the diagonal value as 1 because that says the correlation among themselves, so that will be always 1. And you can also see there are some company or some stock which are having almost zero correlation with all, with all the other companies. So they are not, they are independent, they are behaving as independent, they do not have any relation or correlation with the other company or stocks. Now these as a whole, this average correlation matrix, these represent the market as a whole, but that is not sufficient for us as a researcher, because if I want to give some information or if I want to help someone who is giving money, who is buying asset, selling asset, who is trying to make profit out of it, then we need to see that what is the trend, right? So what we can do that rather than studying the market as a whole, what we can do that we can focus on a specific time period and we can see that what is the trend in terms of the correlation matrix. So we are interested in having correlation matrix time series. So what we can do for that? So
Madam, there is a question you want to answer now or at the end of the talk?
now also I can answer. Is it in the chat box?
Yes, yes, madam.
Okay, 1 minute.
The last.
What are the elements in the matrix? Okay. Uh,
No, before that, there is one question earlier. What does a one correlation mean? The third one.
I cannot. Okay, yeah.
Abhishek Thakur.
What does -1 correlation? -1 correlation means that if say two variables are having -1 correlation, or say if two stocks are having -1 correlation, that means uh, uh, say Coca-Cola and the McDonald. Of course, they will have the positive correlation, but for the example, take Coca-Cola and McDonald, they are having -1 correlation. That means if tomorrow the prices of Coca-Cola stock increases, the McDonald's stock prices will decrease. They will move into opposite direction. Am I clear? Okay, I'll just go for the time being to the second question. What are the elements in the matrix? So correlation matrix one, here I have shown the correlation between the sectors. So here I am just considering the correlation in space. So in the sectors I am talking about, even we can have the correlation in time as well. So here, for what I am showing or what I am interested in is to show the correlation between the stocks or between the sectors. Here, these are the abbreviated form of the sectors, and this color bar, it is showing the correlation coefficient value. Okay, so as now I want to focus on the specific time period, or I want to see the trend, I want to find out the trend. So what we will do, we are having a full time series, right? And we'll divide that into small window. So this one square, this is my window, that can be of any length. For my case, I have considered the window length or epoch of 20 working days length. Now note that we are having weekends, we are having holidays where market remain closed, so we do not have the stock price time series data set for weekend or holiday. So 20 working days, you can think of that it is almost a month. So we are considering 20 working days data set, that is my window length. So now this is my window length or window, and I will calculate the correlation matrix in this specific window. So I'll have one correlation matrix for this specific window. Then I'll shift the window by 1 day, and that also you can vary. So that can be variable, that depends what you want to study. So here, why I have considered 1 day, that is because uh, that will give you the most updated information, which is update means which you can update daily on daily basis. So that is the one point why I have considered 1 day shift. And the second thing is that once I am shifting by 1 day, that will give me a larger ensemble, or that will give me a better statistics. So this is the possible, this is the minimum shift that is possible, right? So because I am considering the daily time series, so that's why I have considered here 1 day shift and window length of 20 days, that is approximately a month's data. So I'll just consider this window, I'll calculate the correlation matrix, then I'll shift my window, again I'll calculate the correlation, and like this I will have different correlation matrix frames like this. Among them I am just here showing 4 for example. So I am having this kind of different correlation matrix frames, and at the above you can see the date. The date specifies, so you see that here I am having a window length of 20 days. So this date is the end date of the window. So 30 October 2000 means that I am taking a 20 days window which ends on 30 October 2000. Like this I will have different correlation matrix frames. Now I am I started with the whole correlation matrix. Now I am considering short time series, and I am calculating correlation matrix. Okay, this will help me to better understand the market, because it will show me how correlation matrix is evolving, but it introduces a problem. What is the problem? That when I was dealing with the whole correlation matrix, I was calculating the eigenvalues, eigenvectors, and that was simple. Once I have the eigenvalues, I can understand the market, and that was uh, easy to do. But when I am now working with the short time series data, that means my n is the number of these sectors, which is 194. N is now greater than t. T is my 20 days window length, right? So n is now greater than t, and so I am now considering the short time series. So I am having very means the time series is very short, so I am not having much information now. There is it is a very short time series, so there is a lot of fluctuation or there is lots of noise, so I cannot calculate the true correlation. There will be a huge noise, and which will uh, if you now calculate the eigenvalues, you will get a huge number of zero eigenvalues due to this noise. Now we have to resolve it. So what we'll do is, we to reduce the noise, we'll use power map technique. What is that? So C is my correlation matrix. So CKL is a specific element on the correlation matrix. We will just lift this degeneracy in the zero eigenvalues by giving a power to the element. We'll keep the sign intact. So for example, say that I am now giving the power as 1.01, and one element in the correlation matrix say is minus zero point 0.2. So I'll keep the sign intact. So if it was negatively correlated, I am not uh, removing that. If it is negatively correlated, now also I'll keep it negatively correlated. So I am keeping the sign intact. I am just giving the power on the map. And sorry for the network issue. Okay, so so what we do to, we are having the noise for when we are dealing with the short time series data, and to deal with that, what we do, that we lift the degeneracy in the eigenvalues by a power, what we do, that we have the correlation matrix element, any element. What we'll do, that we'll keep the sign intact. Sign means that either positive correlation or negative correlation sign denotes, right? So we'll keep the sign intact. If it was negatively correlated, it will be negatively correlated after power mapping. What difference will be there? It will be only the magnitude. We are just reducing this noise, so we are reducing this magnitude by this power. So now you can see that I have used 0.01 or 1.01 as the power, and 0.2 has decreased to 0.1968. So I have reduced the noise, and that was a very standard method. It was first proposed by Vinayak and Thomas in the year of 2013, and that is well proved. And you can see that fact that when I am not using any power mapping, or I am using the power mapping, how, what is the difference, how much smooth it is once you are using the power mapping. But the question is that what is the optimal number of epsilon, optimal power you should use to reduce the noise? Because if you are keeping epsilon 0, that means you are not using any power to reduce the noise. If you use 1 as epsilon, that will, that means you are using actually c square, so it will make of means you will lose some important information. So what should be the value of epsilon that you should use? That is the question. So that I will come after some point. Before going into that, I'll focus on the some other aspect, that now I am having correlation frames which I am generating from co- short time series data, and I have reduced the noise, and I am having a huge number of correlation frames. I want to infer the data or infer the information what I am seeing from these correlation frames, and they are huge in number. So actually we saw that there is a repetition in structure, and that was the first time when it uh, uh, when we encountered this kind of repetition. We thought that whether this repetition is random, or it is having some trend, or there is some variable that is affecting that. So we thought that why not make a cluster of similar kind of correlation structure. And you from the frame itself you can see that this the right most one, it is almost red. uh, am I audible?
Yes, madam. Yes.
Okay, okay, okay. So it is almost red. Red means the market, all the stocks or all the sectors, they are correlated with each other. So the market is waving as one. So that happens during the crash, that all if one market started to fall down during the crash, all the sectors will follow that and will have a crash. So this is the crisis time, and this is the mixed time when they are in between the uh, they are having the high correlation in between themselves or in between a specific sector, but they are not having the inter-sector high correlation. And here we are having very low positive correlation among themselves. Sometimes they are having some few sectors they are showing this redness, and this is the most calm period. So you can see that these correlation frames, they are defining the market state, or uh, whether it is calm or whether uh, it is in crisis, or whether it is just before the crisis. So we thought that if we can group them, and if we can find out the trend, that how it is moving, what is the dynamics of the trend of the correlation matrix, then it will help us when I am going to buy some asset. I am going to if I want to make a profit out of it, then understanding this trend is important. So what we'll do, that we'll make a group of it, and to make a group of it, what is the required information, that which correlation frames are similar, or which correlation frames are dissimilar. So how, when you are when I am having two correlation frames, how we can define the similarity? So we define the similarity by this expression. So Cij at some specific time t1, say this is my t1, and Cij at t2, say this is my Cij t2. If these two frames are similar to each other, then what will be the difference? It will be 0. So we take the absolute difference of the correlation frames, and then we take the average over all the components. That gives us the similarity value. So if they are similar to each other, then it will be 0. If they are having very high difference, say if you are considering this first frame and this last one, they are having a huge difference between them, then you will have a higher value here. And so if say you are considering 4 frames, how many numbers you will have? 4 choose 2, right? So if you are having n frames, you will have n choose 2. And here we are considering the data starting from 1985 to 2016, which is almost 8,000 data points. So if you consider 8,000 data points and you try to calculate the similarity, you will have 8,000 choose 2 data points, and that you can show in this term. So 8,000 choose 2 of diagonal elements you will get. So here the diagonal elements will be of course 0, because it is the similarity among the stock itself. So there is nothing such dissimilarity if you are just talking about the same single correlation frames. That's why this diagonal is 0. But note that it is very high dimensional. We are talking about that 8,000 or 8,000 choose to, that is very much high dimensional. So visualizing it or to extract the information is very difficult. So what we do, we make a multi-dimensional scaling, which is a non-linear dimensional scaling, or non-linear scaling. So what we do, we are talking about 8,000 choose to dimension which we cannot visualize. So we are scaling it down to 2 dimension or 3 dimension which we can visualize. Only the condition is that we'll try to keep the distance between the object fixed as far as possible, and we'll scale it down to 2 dimension or 3 dimension. So it is a 3 dimensional view of this multi-dimensional scaling. And see how clear it is, that you can see here there are some overlapping. So overlapping means that these correlation frames are very similar to each other. Or this, if I talk about 600 and this, so they are very far apart. So just by seeing this, we can say that which correlation frames are similar, which are dissimilar. Now moreover, what we want to do now, we want to make a group of the similar correlation frames, and for that we use a very standard method, k-mean clustering. But when we do the k-mean clustering, we give as input that take k number of clusters. So what should be the optimal number of cluster that you should start with? And we do not have any definite answer that the market should have 1 cluster, 10 cluster, 5 cluster, that we do not have. So we propose a method here to find the optimal number of, or to find the optimal power mapping number, and to find the optimal number of cluster. How we do it, that if you now concentrate on the basic in k-mean clustering method, we start with a random clustering number, and we just go to individual points, and we found that which cluster is nearest one, or which centroid is the nearest one, we just put in that, and like that we make the clustering. So if they are very much distinct or very much far apart, or then uh, whether you are changing the initial condition, that does not matter, because you will always will get the same result. So that means your clustering is very much robust. But that is not the case what happens in the real world complex system, because here the points are very much close to each other, and if you change the initial condition, or that means if you change the position of the centroid, it will give you different clustering results. So how to find out the optimal result out of it? So what we'll do, that we'll start with 1,000 initial, we'll do this problem, we'll repeat it for 1,000 initial condition, and for each initial condition we'll calculate the intracluster distance or mean intracluster distance for each initial condition, and then after 1,000 initial condition we'll find the variance, and we'll check for which cluster, or for which k value we are having that variance minimum. So minimum variance means minimum error. That means your method is the most robust one. But here my problem is two-folded: to find the k and to find epsilon. So we repeat the process for various epsilon and for various k, and we will check for which epsilon and for which k we are having minimum variance. So you can see this table here. I am repeating the process for various k, and this y-axis for various epsilon. And what is these values? These values are the variances of intracluster distances. And we'll now find out that where we are having the minimum variance, and we'll just remove the first four column, because say if I am saying that okay, I'll choose these as my answer, that is for epsilon 0.9 and k as k for 5. But you can see that here for k1 the variance is almost zero. That means it is very much robust. Or maybe for 2 for epsilon 0.7 it is again almost zero. Then why not we are choosing this as our optimal solution? Because market state that cannot have only one state, or that cannot have only two state. It should have minimum 5 state or minimum 4 state. That's why we are not considering k less than 4. We are starting from k equals to 5 to 10, because k greater than 11 does not make sense either. So we are starting from k5 and we are checking that where we are getting the optimal solution, and that for SP500 market, epsilon 0.9 and k5 is the most optimal solution. Now I am just dividing the market, then or I am dividing the correlation matrix frames in 5 clusters, and I am just giving all the clusters different colors. So I had this this map from the similarity matrix, and I am saying that if it is a cluster, if it is a cluster 1, color it by green color. If this is a cluster 2, color it by blue color. And that is how I am getting this. So cluster 1 means green, 2 magenta, 3 yellow, 4 blue, and 5 red. Now this green color means market is at the most calm period. Red means higher mean correlation, so market is at crisis time. And that means if I just plot the whole correlation matrix time series in terms of market state, that it will look like this: that it started with at state 1, it was at state 1 for some time, then it moved to state 2, it again come back to state 1, again move to state 2, again come back, again move, sometimes it is going to s3. So it is just it is continuously evolving. And same thing I am showing it here, that it is sometime it is at market state 1, sometime it is moving to state 2, it is staying at state 2 for a while, and again coming back or going forth like that. So this is the whole picture. Now you can see that at the crisis we are having two arm kind of thing. So it is very obvious, means thing that can come in your mind, that if they are at different place, this is one arm, this is another arm, then if I make the cluster not 5, if I make it 6, then maybe it will come into other cluster, in maybe the 6th cluster. But uh, interestingly, we tried with the sixth cluster, but it didn't come into the sixth cluster. When we tried with the sixth cluster, this broke into two part, but this part was into a single cluster. And that may be because if you just concentrate that this arm, it is a euro crisis, 2011 euro crisis. This is 2015 sell-off crash. One is internal, another is external to the market, and we are not claiming that these two arms are different because one was the internal event, another was the external event, but that may be the reason that uh, that is making them to fall down in a single cluster. We are not, once we are moving from fifth to sixth cluster, it is not even breaking them into two parts. Now most importantly, that from this graph you can now count that how many times it is a state 1, how many times it is moving from state 1 to state 2, how many times it is coming down from S2 to S1, how many times it is going from S1 to S3, and you can make a transition matrix. So in transition matrix, 1 means that when it was 1, it was previously at 1, then it continues to be at state 1 only. 1 2 means it started from state 1, it traveled to state 2, like this. And you can see it was, when it was starting from some state, it was remaining into the same state, that number is very high, and you can define it as the market inertia. And our proposed method practically made this matrix as tri-diagonal. So what is the positive part of this? You see that now what is the count that from state 1 the market state travel to state 5, 0, from state 2 to state 5, 0, state 3 to state 5, again 0. Only there is a non-zero number, that market travel from state 4 to state 5. Now note, state 5 is your crisis state, and our method, we were able to make this as tri-diagonal matrix. That means if today your market is not at the fourth state, you relax, you can invest your money. If today your market is at fourth state, then risk then you have to take the necessary action, that tomorrow you can have risk, you can have crisis. So we practically made this matrix tri-diagonal. So we made probability of market uh, going in from the lower state to the crash state, we made that probability as completely 0. Only if your market today it is at the fourth state, then only stop and take action, and do not invest your money, otherwise you can. So that's this is the same thing for the Nikkei 225 market. I'll just for up to this part, I'll just summarize that we have proposed a early warning system through correlation matrix frames dynamics, which says that the market only you only stop and think if your market is at the fourth state, that is just before the crisis state. So this is the one part. Another part that I want to summarize very quickly, it is a ongoing work but very interesting work, that we all know that water that we all know water phase diagram, that water can have different state, and depending on the pressure and temperature, if you vary the pressure and temperature, we will have different state of water. That is the phase diagram. And we are thinking that financial system, it is very complex, whether and we know that market is moving from the very normal state to crisis state. So can we think this as phase, whether we are also having a phase transition when we are talking about the financial market? Can we have a phase diagram for financial market? If we can have a phase diagram, what will be the variable? Like for water, it is the pressure and temperature, and we started working on it. What we'll do, that we have the correlation matrix frames. We'll just take the square, we'll calculate the eigenvalues and eigenvectors. Now, if the market is at the most calm period, that means it is random. That means it is having disorderness. If market is at crash, then all the market moving in the same direction, they are correlated to each other. That means it is having very less disorder, it is more or less order. So there is, means you, we can have a idea that it is having a order to disorder transition. We just want to have a clear picture of that. So we calculated the eigenvalues and eigenvector, and readily from the eigenvector you can see that it is making the difference between anomaly, bubble, crash and normal from the eigenvector itself. We proceed further, we calculated entropy using the eigenvector. And what we further did, we have the correlation matrix, we separated it out. One is CM. What is CM? CM is the correlation matrix corresponding to maximum lambda. And the rest part is the CGR or the group. So this CM, it the maximum eigenvalue defines the crisis state. So CM thus defines the crisis state, and the dynamics between the sectors or the random fluctuation, everything comes in the C group part. So for CM and CGR, we have calculated entropy. So H is the entropy corresponding to C matrix, HM entropy corresponding to CM matrix, AGR entropy corresponding to CGR matrix. And we plotted H minus HGR versus H minus HM. So these are all the absolute values, absolute differences. We plotted that, and this left side is for the SP 500 market, right side is for the Nikkei 225 market. And you can see that how beautifully it has separated out all the market states. So this red one is your crisis. So at crisis, H almost becomes same as HM, because at the crisis the maximum eigenvalue defines the crisis. So CGR parts become very negligible. So that's why the entropy, the H, that the HM dominates in H at the time of crisis. So H minus HM becomes 0. And this gray color is the random the normal state or the calm period. And you can see that here we have taken randomly two different situation. This blue one is the dot-com bubble time, that it started from the normal state, it entered into bubble state or type 1 and type 2, again it came back. So type 1 and type 2 at two different states of the bubble, you can say. So it again came back to normal. And this is during the crisis, Black Monday crisis, it started at normal state, it market went into crisis, it came to anomaly, and again it came back to the normal state. So it is moving from order, it is moving from disorder to ordered state, again coming back to the disorder. So you can see very clearly the order disorder transition, or we were we are able to have a phase diagram, or we are able to find out the variable to have a phase diagram for our financial market. And then we were trying to have a universal scaling, and we found that if we take h minus hm versus mu graph, these are the exact symbol as we have considered chosen here, that the color symbol is the same, so they are the different market state, and we found that they are having, or they are obeying a universal scaling law, all the market state. And we repeated the work with all the different markets, all the data, and we found different market is also having a universal scaling. So that is the summarize that with that I'll summarize the work that we grouped the market into different state, we proposed the early warning system, and then we show that the market, different market states or different market, they also having order disorder transition, and they obey a universal scaling law. With that, I'll conclude my talk. If you have any question, I'm very happy to answer this.
Thank you, madam. Thank you. So the forum is open for questions, clarifications, doubts. Students, if you have some doubts, you can raise now. Madam, I have some doubts.
Yes, sir.
Doubts. The last slide, you have drawn graph mu versus, what is mu? This mu?
Mu is a mean correlation.
Okay.
So during the crisis, the market behaves like a unit, means they are all correlated to each other. So during crisis, we have very high mean correlation. So that is also clear from the figure that the red one is during the crisis, and it is having very higher mu. So mu is the mean correlation.
And how do you calculate the entropy, the standard expression or entropy?
Yeah, this is the standard expression, as well as it is understandable from the point that as I am saying that when it is normal means it is random, so it is having very high disorder, and the crisis is more ordered, so that this information hides into the in the eigenvector, so that connects disorder order to entropy.
The difference between bubble and normal, what is that?
Bubble is normal is that the market is very random, and if you calculate the mean correlation, that will be zero, so it means ideal case that will be mean correlation should be zero, but it is the come period. And bubble means when I think I have so this picture that one sector that is red, so maybe one sector that is overpriced or overactive, and but it is not affecting the others, so maybe one random sectors are overpriced or overperformed. It may happen that they will grow and burst, and then just vanishes from the market, so that is the bubble.
Oh, thank you, madam. I have one more question, last question.
Yes, yes.
You said some slides before, first state to second state to third state, something like that. So you are going to crisis state, right?
This one?
No. Yeah. Here, you have shown that the last one is the crisis state, right?
Yes, yes.
Is it possible? How do you come back from that crisis state to normal state?
Uh, the market is means when the market is in crisis state, it will try to again come back. It will try to come back to the normal state. So like we had this COVID. So COVID is a different thing, but means a different kind of event happened in the financial market. But still, if we take the COVID as an example, that the financial market was in the crisis state and it tried to recover, and it took time, and it again came back to uh, original, or it came back to the calm period.
My
So
question is whether your model predicts that one crisis state to normal state, something.
No, I am just saying that this is the original time series. I am just proposing the method of having a cluster, or having this transition matrix, uh, and I am just saying that through my method, I have made this transition matrix tri-diagonal. That means I'm just saying that I will give you the trend, that I will calculate the trend, and I will tell you that what is the probability that tomorrow will have crash. How I will tell that, I will have this transition matrix, and you can see that if the market is at state 1, state 2, state 3, there is zero probability that it will go to crisis tomorrow. Only if today the market is at fourth state, then only tomorrow we may have a crisis.
Oh,
That I can tell. So it is the just the early warning system.
thank you, madam. So, question, students, do you need some clarifications? Okay, we are not receiving any questions, madam. So,
Okay.
so since we are not receiving any
Well,
questions, yes, please go ahead.
ma'am, can I ask one question?
Yeah, sure.
Ma'am, how we have predicted this by a time series analysis?
Yes.
So, why? How can we sure that from stage one we cannot get to stage 5 directly, because uh, it can be possible for some stocks to just drop suddenly uh, due to some event or some consequences.
Okay. It is what is state 1 and what is state 5 or what is state 2, that I am defining here, right? So that is by my definition, and that definition involves the method that I am proposing here. I am so there may be a situation that market seemed to be very random, very calm today, but tomorrow something happened and we are having crash. First thing that we cannot have means market cannot just travel from very normal state to crisis suddenly, but say that it is happening. Now what I am saying, that you are giving me the time series, I am having the time series, I am just using my method, I am choosing cluster, and I am choosing my cluster, I am choosing my epsilon, and I am calculating this transition matrix. I am defining my state 1, state 2, state 3, state 4, state 5. That is my definition, and I am saying that according to my definition, according to my method, my proposed method, if I apply that to a time series, I am saying that there, according to my proposed method, there I am finding zero probability that market is going from state 1, state 2, state 3 to state 5. So that depends how you are defining market states.
Is that clear, Abhishek?
Yes, ma'am. Ma'am, actually, there was one stock of Coca-Cola.
Hmm.
So, there was one event happened, uh, and the stock dropped suddenly. So the stock was normal,
Hmm.
and next day the stock dropped suddenly because of that advertisement. Of Cristiano Ronaldo taking the Coca-Cola bottle and just keeping it side. So it caused the stock market to fall suddenly.
A
That
stock market, a stock of the Coca-Cola only,
yeah, yes, ma'am.
not the entered. I am just here talking about the entered stock market. When all the stocks behave at a same manner. So yeah, there may be a fluctuation if you talk about the individual stocks, but here I am talking about the entire market.
Okay, ma'am. Okay.
Madam,
Thank you.
yeah. There is one more question in the chat box. Just to
Okay.
know that.
Okay. Yes. When we considered a short time series, what happens that we do not have the much information available. So when we calculate the time series, that introduces noise or fluctuation. That is understandable, because if you talk about the short time series, there is a huge fluctuation. So if you want to calculate the correlation, it will not give you the true correlation because there is a huge fluctuation. So of course, if you talk about the large time series, it will show less fluctuation, or it will calculate, it can calculate the true correlation. So when you are talking about the short time series, you cannot have the true correlation. In that sense, there will be a huge noise, and large time series will show less fluctuation because more information is available. You are considering large time series, you are considering more information that will help you to calculate the true correlation.
Okay. Kausalya, is that clear? Yeah. Yes. This is okay. So are there more questions? Students, you need more clarifications. Okay. There are no more questions. so, yeah, since there are no more questions, I would like to conclude the session by thanking Dr. Suchetana Sadhukhan for accepting our invitation and giving a very interesting talk on econophysics. Thank you. Thank you very much.
Thank you all for coming to my talk and listening to it.